So last class we talked about polar coordinates, how to graph equations that are given with polar functions, and also derivatives of polar functions. Today we're going to talk about how to work with integrals of polar functions. Now before we do that though, I wanted to look at an example, here it is, where we want to find the intersection between these two graphs, r equals 1 minus 2 cosine theta and r equals 1. Now, based on our previous experience, if we had a function y equals a function of x, and I wanted to know where two graphs intersect, right? If I'm thinking rectangular, usually that would involve just setting the two equations equal to each other. So let's see what it would look like if we did that. Let's take one equation and set that equal to the other equation, 1. Solve this, so move stuff over, negative 2 cosine, should be cosine theta. Negative 2 cosine theta equals 0. Cosine theta equals 0. And so that would occur when theta is equal to pi over 2 and also 3 pi over 2. So it looks like these two graphs intersect at 2 points, pi over 2 and 3 pi over 2. Now, it actually turns out there's a third point. And to see that, let's sketch the graph of r equals 1 minus 2 cosine theta. So as we discussed last class, let's make a t-chart, right? And let's pick some values of theta. As I mentioned before, let's pick values of theta that make the stuff inside of the cosine be 0, pi root 2, pi, etc. And in this case, that would just be 0, pi over 2, pi, 3 pi over 2, and 2 pi. And if I plug those into my equation, when I plug in 0, it would be 1 minus 2, which is negative 1. If I plug in pi over 2, it would just be 1. If I plug in pi, it would be 1 minus, so at pi, cosine is negative 1. So this would become 1 plus 2, which is 3. And then back to 1. And then back to negative 1. So when I graph these, when theta is equal to 0, r is negative 1, so we're back here somewhere. Let me put some tick marks on here just so I know where I'm looking. Okay, so when theta is 0, r is negative 1. As theta goes from 0 to pi over 2, my radius ends up up here at 1. So as theta is increasing, that negative 1 is slowly going down to 0, and then coming up here to 1. As theta goes from pi over 2 to pi, my radius is going out to 3. And then my radius will come back to 1, and then eventually go back to negative 1. So we're getting this shape. So that's the first equation. R equals 1 is the circle of radius 1, so that would be the circle right here, more or less. And notice what we're getting. We are getting intersection points at pi over 2 and 3 pi over 2. But notice that we also have an intersection point here at, well, what is that? Certainly, I would, in rectangular coordinates, this would be 0, 1, 0, negative 1, and this point right here would be negative 1, 0. But here's the reason that we didn't find that intersection point the first time. When I set the two equations equal, when I took the first equation and set it equal to 1, I found all the points where that first equation had a radius of 1. The problem is that missing intersection point was where the radius was negative 1. And I certainly would not have come up with that the method that I used. So I guess the point I'm trying to make here, guys, is that when it comes to polar equations and you want to know where they intersect, don't just rely on the algebra. When you want to know where two graphs intersect, don't just set them equal and solve. You need to actually graph them out, because you may be surprised there may actually be more than one intersection point. So just be careful about that. So today we are going to talk about how to find the area within a polar curve. And the formula we're going to use for that is this one. If we are considering the polar function r equals f of theta, where theta goes from alpha to beta, the area is equal to 1/2 of the integral from alpha to beta of f of theta squared d theta. Clearly more involved than just find the area by doing the integral of the function. It's more than that. I will tell you, this is, number one, it's a formula you're just going to have to memorize. There is an explanation for it. I assume there's an explanation for it in your book. I don't know, I haven't looked. I will tell you that for anyone who goes on to taking Calc 3, either with me next year or in college, we come up with a very eloquent justification of this that makes a lot of sense. Unfortunately, it also involves understanding multivariable calculus and multiple integrals. Yeah, we're not going to do that here. So we're just going to memorize the formula. We're just going to use this formula. But to be able to use this formula, we still need to graph the functions. We still need to see what the graphs look like. Because we need to know what is alpha, what is beta for the region we're looking at. So let's do a few examples. And let's start with this one. Let's find the area of one petal of r equals 3 cosine 3 theta. So the first thing we're going to have to do is graph this. So to graph this, as we did before, I'm going to make a t-chart. Again, I'm going to pick values of theta that make the inside of the cosine be 0, pi over 2, and pi. So theta equals 0 will do it. To make the inside pi over 2, theta would have to be pi over 6. All right, the first case would be 3 cosine of 0. 3 cosine of, well, 3 times pi over 6 is pi over 2. And if I want the next one to say 3 cosine pi, well, to get a pi on the inside, I'm going to need theta to be pi over 3. Okay, and then of course cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1. So we get that. Now, I'm going to need more than this, but let's just start with this. Or actually, maybe I won't need more than this. Let's just start with this. So when theta is 0, I'm going to go out 3 units and put a tick mark. Now, at the angle pi over 6, so let me put that angle pi over 6 here. In fact, let me go backwards also. As long as I'm at it, let me put in the pi over 3 line as well. Okay, so those lines represent theta equals pi over 6 and theta equals pi over 3. By the time theta goes from 0 to pi over 6, my radius is going down to 0. And then as theta goes from pi over 6 to pi over 3, so that would be here I'll have to erase this, but as theta goes from pi over 6 to pi over 3, my radius is going negative. So actually we're going to be back here. So I'm going to go from a radius of 0 out to a radius of 3. And then I didn't work it out here. I guess I could here. When theta is, let's see, I want this to be 3 cosine. I want to get 3 pi over 2 inside. So I need a pi over 2 on the inside. So it goes back to 0. So by the time my angle goes from pi over 3 to pi over 2, in other words, down here, because the radius is negative, by the time that the theta goes to pi over 2, my radius is going to come back to 0. Now, I could fill in the rest of this, and I believe it would look something like this. Now, but I mean, to realize that, I would have to fill in the rest of this t-chart. And I want to point out that we don't really need to do that. So to find the area, I know I'm going to set up an integral. I know it's going to be the integral. I need more space than that. I know it's going to be the integral of 1/2 of my equation, 3 cosine 3 theta, squared d theta. And really, the only question I need to answer here, because those are I already know this. The real question I need to ask is, what are my endpoints? What are my boundaries? Now, the first suggestion I'm going to make is only pick boundaries, only pick regions where the radius is positive. And I say that only because if the radius is negative, it's possible that weird things could happen. Just don't do it. My suggestion would be only pick parts where the radius is positive. So when I filled in the rest of that graph, I did get a leaf on the bottom, right? Or a petal, whatever it's called, I don't know. I did get a petal on the bottom, but notice that in that petal, this was the part where the radius was negative. So I'm going to try to avoid that. What I'm going to do instead is notice that I get another petal if I realize that the first part of my interval, the first part of my graph, has a mirror on the bottom. There is symmetry going on here. Okay, there is symmetry. So rather than finding the area of one petal, what we could do is find the area of that first little bit. And that first little bit was when theta went from 0 to pi over 6. But of course, that's not an entire petal. That's only half a petal. So what do? We double it. The integral that I've set up finds the area of that half a petal that I've shaded. But now when I double it, now I'm getting the entire petal. Okay. You heard me say this a lot back in chapter 8, but the hard part of these problems is setting up the integral. Now we need to evaluate it. And we do need to talk about that. Obviously the 2 and the 1/2 cancel, so that's kind of nice. And this turns into the integral from 0 to pi over 6 of 9 cosine squared of 3 theta. And now we get to the question of, okay, how do we evaluate this integral? And to evaluate this integral, we are going to have to remember how to integrate trig functions. And some of you may have already picked up on the fact that, oh, look, the cosine is being squared. When we integrated trig functions and the sine or cosine were being squared, we used the double angle identity. Cosine squared becomes 1/2, so I'll leave the 9 there, so 9/2 of 1 plus the cosine of twice the previous angle. So if the previous angle was 3 theta, then this becomes cosine of 6 theta. Yes, we are going to have to remember how to do all those integrals that we did a couple chapters ago. From here we can integrate. So the 9/2 is multiplied by, so it'd be theta plus 1/6, sorry, sine of 6 theta from 0 to pi over 6. So we get 9 over 2 times, when I plug in pi over 6, I get pi over 6 plus 1/6 pi, put 1/6 sine of pi. minus 9/2 times 0 minus 0, because of course the sine of 0 is 0. Sine of pi is also 0. So what I end up getting is just 9/2 times pi over 6, or if I reduce this, 3 pi over 4. So the area of that region is 3 pi over 4. Polar functions have a lot of symmetry, and we can definitely use that to our advantage. And so that's exactly what we did. We just found the area, or we just set up the integral for the top function, and then we doubled it. If we wanted to, this black portion down here at the bottom, we could have picked that up by letting theta run backwards. Rather than the integral from 0 to pi over 6, we could have done instead the integral from negative pi over 6 to positive pi over 6. If we did that, then there would not be a 2 out in front, and we'd still have the 1/2 times the function squared. Okay, it doesn't matter whichever one you want to do is fine, and I suspect most of you guys will like that symmetry using that. All right, let's try this problem. Find the area between the inner and outer loops of the curve r equals 1 minus 2 cosine theta. Well, fortunately, we've already graphed this one, so let's do that. When we graphed it, we started at -1. We went back to 3, and then we went back there. So this is the graph we did at the beginning of the lesson. Okay, so we want to find the area of the area between the inner and outer loops. So let's start with, well, let's start with this. I don't actually know what this point right here is. I don't actually know where the radius is gonna be 0. So let's start by asking that question. Where is the radius 0? Let's set the radius equal to 0. We're going to get cosine theta is equal to 1/2. And so that will happen when theta is equal to pi over 3. And also the one on the bottom, that's what, 5 pi over 3? But that's okay, that's pi over 3. So where this graph stops having a negative radius and starts having a positive radius is right here at pi over 3. Now, again, I'm going to use some symmetry. I'm going to find the area of this graph from pi over 3 over to pi. I'm going to find the area of this whole thing. Now please notice, I'm starting at pi over 3, so as far as that's concerned, there is no inner loop. I still need to worry about that later on. I'm just going to find the area of the outer loop. So to do that, I'm going to set up, it's going to be the integral from pi over 3 to pi, 1/2 of the function squared, and of course this only gives me the top half. I want the whole thing, I want top and bottom, so I am going to double that. That gives me everything that's inside of the big loop. So now we're going to have to subtract the area of the inner loop. Sure, why not? Okay. So we have to subtract the area of the inner loop. Notice that the inner loop, so let me erase this part now. Notice that the inner loop comes from this beginning part where the radius was negative. So that would occur, so now we're going to subtract because we're finding the area here. That will give us the interval from 0 to pi over 3. And it's the same function, 1 minus 2 cosine theta squared. Oh, I forgot the 1/2, sorry. So we got 1/2 the integral from 0 to pi over 3. Again, 0 to pi over 3 only gives me the top half. If I want the whole thing, I'm going to have to double it. Yes, I know I'm using the part where the radius is negative. I don't really have much choice in this case. On the last one, we had a choice. So let's pick the region where the radius is positive. But if the only way we're getting that inner loop is where the radius is negative. And so we have to set it up this way. And it'll work out fine. It'll be okay. I'm not going to work out the rest of this problem, except to cancel the 2's and the 1/2's, because it's just fun. I'm not going to work out the rest of this problem. I will briefly point out, though, that when you find the antiderivative of 1 minus 2 cosine theta squared, first of all, you're going to have to FOIL it out. So it'll be 1 minus 4 cosine theta plus 4 cosine squared theta. And then to integrate that, to integrate cosine squared, we're going to have to now use that half angle identity. So it'll be 1 minus 4 cosine theta plus 4 times, and then cosine squared theta becomes 1/2 of 1 plus cosine 2 theta. Okay, so I'll leave it as that. From here, distribute, combine terms if you want to, and then integrate it. And then, of course, there are endpoints. All right, so here's our next one. We want to find the area that is inside r equals 3 sine theta and outside r equals 1 plus sine theta. Well, we're going to have to graph them again. So here, I'll make this one blue. So I'll pick some thetas. And 3 sine theta. Some good thetas here would be 0, pi over 2, pi, 3 pi over 2, and 2 pi. And so sine of theta is 0, sine of pi over 2 is 1, sine of pi is 0. So 3 pi over 2 is -1, and sine of 2 pi is 0 again. And just so we've got it all in the same place, this will be 1 plus sine theta. So again, sine of theta is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, and then sine of 2 pi is 0 again. Okay. So 0, 0. By the time theta goes from 0 up to pi over 2, we've got a radius of 3, so we're out 3 units. By the time theta goes from pi over 2 down to pi, the radius goes back down to 0. So I don't even need those two. There are the last 2 points on the bottom. And then my last one here, when theta is 0, my radius is 1, so that's right here. By the time we get to pi over 2, my radius is 2. And then my radius comes back down to 1. And then my radius goes to 0, and then goes back out to 1. Oh, it's a heart. Good thing I did it in red. Okay, it's not a heart. It is a cardioid. That is the literal, yeah, anyway. Okay, so we want everything that is inside the blue graph and outside the red graph. All right, inside the blue and outside the red means we're looking at this region right here. Okay. Well, I have a big question, and that would be, where do these graphs intersect? What are these intersection points? Here and here. So to answer that question, we're going to need to set the equations equal. So 3 sine theta is equal to 1 plus sine theta. So 2 sine theta equals 1. Sine theta equals 1/2. And so theta is going to be, let's see, sine is 1/2 at pi over 6. And again at 5 pi over 6. Okay, so those are my intersection points. And so to find this area, let's see here. Yeah, to find this area, I'm going to have to find the area that's inside the blue part. So that would be, well, again, we could use symmetry here if we wanted to, not a bad idea. If I found the area, so it's 1/2, the blue one was 3 sine theta. So it'd be 1/2 of that function squared d theta. If I were to go from pi over 6 to pi over 2, that would give me the right half, but then I could double it. So that works. So that gives me everything that's inside of the blue graph. And now I want to subtract everything in the red graph, so minus, I'll do the same thing. 2 times the integral from pi over 6 to pi over 2. This time my function is 1 plus sine theta squared. Okay. So there's our setup. As we've seen in previous chapters, maybe they'll just say set up but do not evaluate. If so, great, there's our answer. If we do have to finish this off, okay, we've already done a couple. The blue one here becomes sine squared, use the double angle identity. The red one, FOIL it out, and then you'll need a double angle identity for that one as well. Okay, but we got it. So I want to take a minute and look at an example from a previous AP test. And so we're going to do, this has 4 parts to it, so we're going to do all 4 parts. And let's see, so for this problem, the curve is described by the equation r equals theta plus sine of 2 theta. And we're asked a number of different things. Notice we are given the graph of the equation. And so for part A, we're asked to find the area bounded by the curve and the x-axis. Okay, well, to find the area bounded by the curve and the x-axis, so we want everything that's inside of the curve. And so it looks like we're going to set up the integral from 0 to pi, 1/2 of my function, my equation here, theta plus sine 2 theta squared d theta. Now, there is one thing that I forgot to mention about this problem. It is a calculator problem, which means we can just finish this using Math 9. When we use our calculators for this, first of all, please make sure you are in radian mode, always radian mode in this class. Second thing is this. I realize that what we're given is a polar function. However, to do this problem, we do not need to switch our calculators to polar mode because it doesn't matter that it's a polar function. It is a function of a variable. We are integrating with respect to that variable. And when I type this into my calculator, instead of theta, I'm just going to write x. When you're using Math 9 to do an integral, it doesn't matter what the variable is. I could set up the integral as, I don't know, a function of t and then do dt, or w, then do dw. It doesn't really matter. So when I type this into my calculator, I'm doing the integral of 1/2 of x plus sine 2x, quantity squared, dx. Anyway, I'm getting an answer of 4.382. Okay, so there's my calculator or my answer from the calculator. As always, make sure you set up the integral, tell me the endpoints, tell me the integrand, meaning what function you're integrating. Don't forget that 1/2, and then we use Math 9 to come up with an answer. Okay, here's part B. Find the angle theta that corresponds to the point with x-coordinate -2. Okay. With x-coordinate -2. Okay, so not that it helps us any, but here it is, right here. That's nice. There's x is -2. To answer this question, we're going to have to remember basically parametric. We're going to have to remember that x equals r cosine theta. Well, r would be the equation, theta plus sine of 2 theta. So there's r cosine theta. And then, not that we're going to use it here, but maybe we will in a minute. Y is equal to r times the sine of theta. And so when I'm asking you to find the theta that corresponds to the point where the x-coordinate is -2, what I'm really saying is, hey, set the x equation equal to -2, and now let's solve that equation. So here's my calculator, and when I solve this equation, I'm just solving an equation. I don't really care this theta. I just want to know, when is this function equal to 2? So on my calculator, I'm actually just going to graph, let me just type it in. It'll be x plus sine of 2x. Okay, so there's my r, cosine x. And I'm going to write +2. Basically, I'm going to move everything over, and so that the whole thing. So really, now my question is, when is this equal to 0? I'm going to graph it. I would point out that the point that I identified. Let me move this over here. The point that I identified. Notice that the theta that I want is between pi/2 and pi. So the angle that I'm looking for is going to be less than 3. Well, there it is. Crosses at a point less than 3. Well, less than 3.14, but in this case it's less than 3. I'm going to calculate that 0. So I'm going to calculate the 0 of this function. My left bound, how about 2? My right bound, how about 3? Guess, there it is. So the point that I'm looking for, when the variable, now when I graphed it, my variable was x. In the actual problem, the variable was theta. And the value of that variable was 2.786. So when theta is equal to 2.786, there we go. All right, let me bring this down here. Let's move on to part C. I've got the graph reprinted there at the bottom, and then the equation is at the top. R equals theta plus sine 2 theta. And the problem says, for theta between pi/3 and 2pi/3, dr over d theta is negative. Now, we're not actually asked to prove that. We could if we wanted to. They just saved us the effort. But if we were to take the derivative, notice it says dr over d theta. So if I were to take the derivative of this equation with respect to theta, it would be 1 plus cosine of 2 theta times 2. And not that we're going to go into it, but I guess that's negative for theta between pi/3 and 2pi/3. Again, please notice this dr over d theta is not dr over dt or dy over dx. It's the derivative of r with respect to its variable theta, dr over d theta. And so anyway, we haven't even finished reading the problem. It says, what does this say about the curve? Well, dr over d theta is the change of the radius as theta increases. Okay, this is the change of radius over the change of angle. And if and d, the variable is always, we always assume the variable is increasing, so theta is increasing. And if this is negative, that means that there's going to be a negative change in radius as the angle gets bigger. A negative change in radius, that just means the graph is getting closer to the origin. So if I were, so I'm asked, what does it say about the curve? Well, it says that as theta increases, r is getting smaller, which means that the graph is getting closer to the origin. And we can kind of see this was sort of the region that we're talking about here, between pi over 3 and 2 pi over 3. And certainly we can see that. I'm not interested in the fact that it's getting smaller, they're lower. I'm not interested that the y-coordinate is decreasing. What I'm interested in is that the points are getting closer to the origin because the radius is decreasing as theta goes on, as theta increases. All right, for part D here, the particle is moving along the curve so that its position is x of t, y of t, and such that d theta over dt is equal to 5. We want to find dy over dt at the instant that theta is equal to pi over 2, and we want to interpret the answer. Okay, so the particle is moving along the curve so that this is its position, x of t, y of t. Let's see, as such that d theta over dt is equal to 5. Okay. So we saw on the previous slide, and we wrote this out already, that x was equal to r, but the r was the equation, theta plus sine 2 theta. So r times cosine theta. And y is equal to r times sine theta. Okay. The problem is asking us to find dy over dt. Now, notice that y is not expressed as a function of t, it's expressed as a function of x. But certainly, as time goes on, the theta is changing. In fact, we even are told the theta is increasing by 5 units as time goes on. The theta is increasing by 5 units for each 1 unit of time, whatever that happens to be. And so I'm not asking for dy over d theta, I'm asking for dy over dt. Basically, I'm going to take the derivative of the y equation with respect to time. This should feel sort of, kind of like a related rates problem. Not exactly, but kind of. And so I'm going to take the derivative of this equation with respect to time. The derivative of y with respect to time is dy over dt. The derivative of the the derivative of the right side with respect to time. Now, there is a product rule going on here. Can we agree? No, let's just take the derivative. It's all right. So to be the first times the derivative of the second plus the second times the derivative of the first. So that would be 1 plus 2 cosine 2 theta. Now, here's the thing to keep in mind. That is the derivative of this function with respect to theta. But didn't I say we were taking the derivative with respect to t? If you'll remember related rates problems, we're going to take the derivative, but then we multiply that by, in this case, d theta over dt. Right? If I wanted dy over d theta, I would have been done, but I wanted dy over dt. And so it's with respect to a different variable, and so I need to multiply by this extra stuff. Now, we are given pi over 2. That makes life nice because, well, here theta is pi over 2. That makes things nice because this gives us the sine of pi, which is 0. Cosine of pi over 2 is 0. sine of pi over 2 is 1. Cosine of pi is -1. And then times d theta over dt, which we're told is 5. And if I work all that out, it looks like I'm getting an answer of, I believe it's -5. Yeah. So the value of pi over 2 is nice. Okay, so, and now the problem, the last thing says, interpret your answer. Okay, what does this represent? Well, this is dy over dt. As the particle is moving along the curve, this represents the rate at which the y coordinate is changing as time goes along. So as time goes on, and I don't have units for distance or time, but this would be represented as -5 units of distance divided by units of time. As time goes on, at this moment, the y coordinate is decreasing at a rate of 5 units per second or minute or whatever it is. So this represents how quickly the y coordinate is changing. In part C, it was the rate of change of the radius as theta increases. Here we're talking about the rate of change of the y coordinate as time increases, as time goes on. Okay, that brings us to the end of this example. And again, this example is a good example of an AP question. When it comes to calculus problems in polar coordinates, these are some very typical types of problems that I've seen lately. So they're definitely worth understanding. So this is the end of chapter P, this chapter. This is the last lesson for this chapter. So next class you will be reviewing, and the following class is going to be the chapter test.